Hello everyone. Hello Vedika. Good evening Anjali. Hello Piyush. Good evening Nancy. Hello everyone. We will start in some time. We'll start in just 2 minutes. Hello. Good evening Gaurav. Good evening Amlesh. Good evening Devika. We start in 2 minutes. Today we have to do. Firstly, we have to do the problem which we left on, which was split array largest sum. Then we have to introduce us to ourselves to some uh, to a problem to a technique known as sliding window. We'll do some problems on slide and then we will see how we can solve some really tough problems using that technique. Good evening, Shan. Good evening. Good evening, Nancy. We'll start this in a while. Okay, so welcome everyone to day 5 of the Array Bootcamp. Today we will be talking about the last problem we left on the previous session, which was split array largest sum. It will be ending our problem set of binary search. We'll be ending it on binary search on answer, a very important concept. We have done some problems. I guess we have done decent amount of problems. Started with Coco eating bananas, and now we have done this third problem of binary search on answer. I believe you guys will be pretty confident this is a hard lead code hard problem. Then we will discuss the new technique, not new. You will realize we were using it, but we'll just name it and define it properly in this session, which is known as sliding window or two pointer. And then we will do a basic problem of two pointer. Then we'll see a very popular problem known as trapping rainwater, right? So this is the blueprint of today's session. Let's start with the first problem of the day, which will be split array largest sum. And oops, here is the problem. Given an array nums and an integer k, split nums into k non-empty subarrays such that the largest sum of any subarray is minimized. Think about this problem. Think about how you can approach it. Try to write it in the chat. What you are thinking. What's your approach? Any observation. Try to note it down. Even if you don't have a pen or paper, use chat as your notebook and just write whatever. you are observing in this problem. Let me show you the constraints. This is the constraint. Honestly, you don't really need those constraints. No, I'm saying just give me a generalized algorithm to solve this problem. I'm not saying to solve this example. Someone just gave the answer 18. When I'm asking a generalized algorithm, like whatever you're thinking in this problem. Okay. Considering the scarcity of time, I feel like we should discuss it. Hello, Manish. Good evening. So, just to give you a quick recap, Manish, we are doing the last problem of binary search on answer. Then we'll be moving up to solving some really tough problems like, okay, Benny, okay. So, the question is, let, just, let me just see the problem. Let array largest sum. Is that the largest sum we have is minimized. Okay. Now notice that every entry is positive. Okay. We will be using this fact. Okay. So first observation. Let me just write the summary of the problem. Split in case subarrays such that maximum sum of subarray is minimized. Okay. So first observation, which would be all entries inside nums are positive. This is the first observation. We'll be using this observation a lot. Using this observation a lot. Okay. Now, what can we know? They're saying maximum subarray is minimized. See, let me give you just a advice for future. Any such problem of maximizing the minimum or minimizing the maximum, okay, always try to think of a binary search. This is just my this is just my experience with such problems. I mean, uh, sometimes they can be DP problems as well, but my experience says that mostly they are binary. They are solved by binary search. Like whenever you are asked to calculate maximum of the minimums of any entity, here we are talking about sum. So if any entity, try to give binary search a shot, because like in this problem as well, there is no clear idea why binary search will be used, right? There is no as such clear idea. So these are some, that's why we solve many problems. We try to extract patterns because see, um interviewer will only be asking you from a interviewer has a finite bag, right? This is a finite bag that had something like 70 patterns, maybe 70. I'm saying like they're a very large number. Let's say 28 patterns. Let's say you just have to solve. You have to like be clear in those patterns. So what's the pattern? See, um, Coco eating bananas. You can you could have imagined this as minimum speed to eat all bananas. This was the problem, right? This is one pattern. Okay. So what I'm thinking is, let us just enumerate some. Let's just try to answer this problem, enumerating some. Let's just try to answer this problem for every value of the sum. Let's try to answer this problem. What number of subarrays we need such that max of sum is less than equal to s, and s will be any entry from here. Let's say this is s for now. Okay, now this will be the question we'll be trying to ask. Let's say this comes out to be capital M. Now if this capital M is less than equal to k, we need less than k divisions within less than or equal to k divisions. You can create subarrays such that maximum of the sum of these subarrays is less than equal to s. This means you can create k divisions such that s will be your upper bound, right? Think about it. Let me give you an example, a very simple and short example. Let's say my k is equal to 2. Okay, and I choose my s to be equal to, let's say I choose my s to be equal to 28. Now note that the sum of this array is equal to 27. So how will I calculate how many subarrays I want? I will just keep a current variable. I will keep accumulating sum like this, right? And whenever my cumulative sum reaches greater than my cap, imagine this as the cap. This is the cap. We cannot have more than s sum of a subarray. We make this current 0, which essentially means we have created a division. This is our first division, let's say, right? Okay. So think about it. For s is equal to 28, I can just have one sub array and it will be enough, right? Now what I claim is if m, now in this case m is coming out to be 1. If m is less than equal to k, then we can create divisions. Why? Because we know that all the entries are positive. So if this is 28, if this is 27, I create any division. We know this will be less than equal to 27. This will also be less than equal to 27. There can be a case when these are zeros. They are not zeros here. There can be a case where they are zeros, right? So this condition is important. Now let's just take s equal to 20, s equal to 15, let's say, and k equal to 3. Let's just solve this problem for not s is equal to 15. Let's take s equal to 9. Now focus. Okay, I need your focus, guys. Come on. 3, 7. Now it's coming out to be 12, which is greater than 9. So we know we can't have this subarray, can't have this subarray because this is the cap. So we create a division here and we mark it as 5 because now we are creating a new subarray from here, right? Now we see 11. Can't have 11. No, can't have 11. Greater than. So we create another division like this. Mark it as 6. We come here, it is coming out to be 10. It is 9. We can't have this. We can't have this subarray. Hence, create a division like this. We come here, 4. And now we see 4 plus 5 equal to 9. We can have this. Hence, for this case, m equal to 4, which is greater than k. This means s cannot be the minimum largest sum. This value will be greater than 9. Because for 9 we are not able to create less than k divisions. We created 4 divisions, right? Just going greedily while creating divisions, right? I hope it is clear to all how we are creating our divisions and all. Now let's jump on to the code of this problem. We initialize our initial answer with r, which is the maximum sum, right? Because we know that will always be the answer, right? We can have one division for it, which is the whole array. That's always the answer. We are asked to minimize the maximum subarray sum. So r equal to sum of the whole array is a safe choice to have, right? The rightmost. The leftmost element will be the maximum element of A. I can keep it 0 as well, there is no issue. And see, we are doing the same thing. This count represents the number of subarrays. This is now just implementation stuff. This is quite simple. Just implementation stuff, right? If count is less than equal to k, we decrease our limit r equal to m. If it is greater than k, then we increase our left limit, which denotes values equal to this and less than them will never be in the answer. Values equal to r and greater than r will always satisfy. Hence, when it satisfies, we are initializing r equal to m, and when it is not satisfied, we are initializing l equal to m. I hope it's clear to all. We run this. I hope this will be accepted. Just this will be accepted. Yes, it's accepted. If anyone has any doubt, they can ask in the chat. Prakash says, please explain the techniques. Okay, I will explain the technique once again. Till then, I am posting this. Attendance link. Uh, it is there in the chat. Okay, I hope uh, everyone has marked the attendance till now. Let's try and understand this code. I guess a lot of people were confused in this. So simply, we are initializing two pointers. One is L, other one is R. L denotes all the values equal to and less than L will not be accepted, which means for that value of the sum, it is not possible to create k divisions, right? It is not possible to create k divisions. Not possible to create k divisions for the values equal to L and less than L. Hence, uh, we defined our L to be equal to max element minus 1, because then that max element will have no place to go, right? Hence, trivially, we know that for any value of sum which is less than the max element, it is not possible to create such divisions, because every subarray, the maximum value of the sum of subarrays will be at least the maximum element of the array, right? Because there has to be some subarray which creates that maximum, which contains that maximum element. That is the reason of putting the L limit to maximum element, right? R is Rh limit shows the values equal to R and greater than R will always be the answer. Why I've kept R equal to sum of the array? It's because see, uh, quotient only makes sense if k is at least 1, right? If k is 0, then the quotient itself doesn't make any sense. To create zero divisions, it makes no sense. Has to be at least one subarray, right? There cannot be zero subarrays. And in order to have one subarray, there which will have which is the case where we will having largest sum, considering that all the weights are positive. Uh, the value of the largest sum will be the sum of the array itself, right? Hence, the safest correct limit to take for the values equal to R and greater than R, which always satisfy, is equal to the sum of the array, right? And now we are simply applying our standard binary search. The count variable counts the number of subarrays such that their sum are capped by this m, right? So whenever the sum is getting greater than m, we are we are initializing current to 0 and then increasing the count. It is just my way to implement this solution. You can have your own way. I feel like this is the most simplest way to implement. And then in the end, we are checking if the number of subarrays are less than equal to k. If they are less than equal to k, then there is always a way to divide this array such that the maximum sum of the subarray is always less than equal to m, right? So we put r equal to m and l equal to m. L equal to m if it's not possible, if the count is greater than k. And then at the end we return r, because what was r? Remember, the definition of r was the values equal to r and greater than r will always be accepted. And what we were asked to find? We were asked to find the minimum value which was getting accepted. So r is the answer, right? Trivially. Okay. So I believe it is time for really time to introduce this really amazing concept of sliding window slash two pointer technique, right? So it's nothing, just property. Moving it, new property gets violated. Right. So what you will basically doing is we will be initializing two pointers. They will satisfy some property, and whenever that property is whenever that property gets violated, you basically change the position of this pointer. Simple as that. Let's try to look at one problem. Longest substring with no repeating character. Try to think about this problem, try to read it. Pretty simple, right? We'll simply see. This is very intuitive, very intuitive actually. Okay, first we initialize our pointer. Okay, we initialize our both of the pointers like this. Both the pointers are on A. We move this second pointer. I will denote the second pointer, the green one. This is a valid arrangement, right? No repeating character. Keep your answer variable to be equal to 3. because no repeating character. Let's just keep a DNA. Okay, then you increase your pointer to here. Now see, the alarm bell should be ringing because we found a repeating character. This repeating, the nature of a character being repeated can be easily judged by an ordered set. I guess by now we have uh, been really comfortable with an ordered set. Hence, we need to adjust our window size. We see this character is repeated. We shrink our window till we find an optimal window. Shrink the window, right? So we shrink our window. We make our window like this. You see, yes, this is an optimal window. But we don't really need to update our answer because answer is already 3. Okay. Again, we move up. Again, alarm bells start to ring because this is again a repeating character. We need to fix it. This is not the optimal window. We again shrink our window. Shrink our window to this. Again, we find that this is the optimal window, but the size is again 3. The answer variable is already initialized to 3. We don't update it. Then again move to B. Again alarm bells ring because this is again not an optimal window. We have repeating characters, and this time we move this pointer. We move this pointer to here. Why? Because in this substring there is only we can only move this pointer to here to get an optimal window. This is an optimal window, right? So answer is 1. We don't update the for this the temporary answer is 1. We don't update the global answer. Why? Because 1 is less than 3. We need the maximum value. Now we move our second pointer till here. We again check this is the optimal window, but again this window has size 2 and we already found a window of size 3, hence we don't update the global variable. Oops. Now we move our pointer to here. Again alarm bell should ring because this is not the ideal situation. It contains a repeating character which is B. So we should be increasing our left pointer, increasing it to here. Now see, we found an optimal window, but again its size is 2, right? Hence we don't update this. Now see, if we again increase this, again we see this is again an optimal window, but again size is 3 and global variable already has 3, so we don't update it. We again increase the right pointer because we find an optimal window. Whenever we're finding an optimal window, we are increasing the rightmost pointer. If the window is not optimal, then we are shrinking the window by increasing the left pointer to find the optimal window. And now this is the most optimal window we found, which has the size of 4. The global variable is 3, hence we update it to 4. Hence the answer for this comes out to be 4. Right? I hope that the algorithm is clear to all. We have done step by step algorithm for this problem. Time to code it up. Here is the code for the problem. First, we are for finding the initial window, and now see. size of the window. I hope this is clear. This is the shrinking step. This is expanding step. Very, very easy problem. Very, very standard problem. A very important problem to understand sliding window. Right? Although this this problem is not of arrays, but you can uh, imagine string as an array of characters, right? Still a problem of array. See, this problem could have been largest subarray with non-repeating digits or numbers. Could have been like this, right? That there is no issue right there. I hope this problem is also clear to you all. Very simple problem. If there is any doubt, you can ask in the chat. We have written very concise code for this. Lead code problem number, Shaurya is asking. Shaurya, this is third lead code number problem, third. So, okay. Let's move on to the my personal favorite problem. When I realized this can be solved by two pointers, I was like shocked because I will discuss two approaches. First, I'll discuss my approach, which I thought while solving, and second approach, which I saw online through various sources. And I realized there is a two-pointer solution. The problem which we'll be discussing now is trapping rainwater. So you are giving n non-negative integer representing an elevation map where the width of each bar is 1. Compute how much water it can trap after raining. See, it's a very interesting problem. Let's simply let us simply the problem is known as trapping rainwater. Uh, just wait a second. I am just noting it down. 010 210 132121. All right, so this is the problem, right? See, a very simple solution of this problem can be you store the prefix maximum. You store the suffix maximum, yes, which will be what is suffix maximum? Maximum till this. Consider all the values. Consider all the values from for maximum of I. Consider all the values till here. and take the maximum out of them, which is 3. So a prefix maximum, suffix maximum would be 2, 2, 2, 3, 3, 3, 3, 3, 3, 3. This would be suffix maximum array, right? Similarly, create a prefix maximum array. 1, 1, 2, 2, 2, 3, 3, 3, 3. This would be prefix maximum array. Now, guys, see very, very amazing thing. There will be a very amazing thing here. 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 3. So we can map to all of these values, right? Similarly, we will keep a suffix maximum. Oops, wrong choice. Similarly, we keep a suffix maximum. Suffix maximum would be 2, 2, 2, 3, 3, 3, 3, 3, 3, 3. And now look, for every position, how much water it can store, it will always be minimum of these values. So amazing, right? Because it needs a wall, right? It every column needs a wall to store water. And if this wall would have been one, this water would have flown. This water would have flown. All of this water would have flown, right? So we calculate water in every column, and what will it be? The left maximum, right maximum, and the minimum of those maximums. Do you understand? Because we need a wall to store water, right? If this wall will be shorter, water will be till the height of this wall, because it cannot go up more than this, because it will overflow from this side. Are you trying to understand? So just keep two variables, prefix maximum. This is suffix maximum. Simple, a easy problem can be solved very simply by the notion of prefix and suffix. Just it's the first time we are seeing prefix maximum. We were seeing prefix sum, suffix sum. This is the first time we are looking at prefix maximum. It's so amazing, right? The idea was for every column you are calculating, let's say for this column, you take the minimum of them, that will be the answer, because water cannot go up till the height of the right maximum. It will flow from this, overflow from this. We have to take the minimum of the maximums, right? Same goes for this. I hope this is clear. It was a tough problem which was made simple by a very smart implementation. You can see the two-pointer implementation of this problem on your screen. Pretty simple. Left maximum, right maximum, taking the minimums of the maximums and adding them to the answer. Do let me know if you have any doubt in this problem. Problem was made pretty simple by by just the idea of prefix maximum and suffix maximum, right? This was a hard problem. It was a hard lead code problem. Surya says it's clear to him. Very nice. Very nice, guys. If you are able to tackle hard problems by now, it's amazing. Exactly, Nancy, is not very hard. The partial, the first problem we did, the maximum one, that was harder than this problem, right? Because I was teaching you binary search on answer, so you guys were able to, like, it was able, you were able to strike that, okay, we'll use binary search on answer, but it's not easy to understand if you're given a problem in the contest, for example, or just an OA, online assessment. It's not easy to, you know, uh, to get that binary search will be used there. But in this problem, I feel like it is simple. I hope it's clear to everyone. It's clear to Mayank, to Ashish, very nice guys. To clear to Vaishnavi. Yes. So I hope that you guys enjoy today's session. With this session, we have thoroughly completed all the major techniques used in arrays problems. Uh, there were some more techniques which we could have explored, but I think they will go out of the scope. I was thinking of exploring some combinatorics problems, but maybe someday later we will be able to do them. Nancy says, tell us about something about certificate. I guess if you have done all the 5 days, certificate would be given on the basis of attendance. If you have done all the 5 days, then you will get certificate. Yes. So keep practicing, everyone. Uh, with this problem, I would like to mark the end of this bootcamp. Uh, yes, I hope you guys enjoyed the bootcamp. Okay. Thank you, everyone. Thank you. Thank you. Bye, everyone.